All right, so homework assignment number 2 for the week. We have practice problems from the problem set PDF. And these are mostly about kinetic energy, although later on we get some linear motion stuff thrown in there as well. So starting off, number 7, a car with a mass of 1250 kilograms, 26 meters per second. Kinetic energy is what? So we're given mass, 1250 kilograms. Given velocity, 26 meters per second, asked for kinetic energy. Kinetic energy formula, 1/2 mv squared. Plug in, chug out, 1250 times 26 squared divided by 2. It's 422,500 joules. Boom, done. Number 2, what would the kinetic energy be of a bullet with a mass of 22 grams? Let's convert that into kilograms. That's 0.022 kilograms. And a velocity of 650 meters per second. What is its kinetic energy? Kinetic energy, 1/2 mv squared. Plug in, chug out, 1/2 m v squared. 4,647.5 joules. Pretty straightforward plug and chug stuff so far. Next one, we are given mass of a bowling ball, 4.4 kilograms. We're given its kinetic energy, 185 joules. And in this case, we're asked for velocity. So same formula, K equals 1/2 mv squared. But in this case, we're solving for velocity. So that velocity is going to be the square root of 2K over m. Plug in, chug out. K over m, and then the square root of that, 9.17 meters per second. So far so good. That's like your warm-up on basics of how to use the kinetic energy formula. Good times were had by all. Why? There we go. Okay, so now we get into a little more detail here, incorporating energy with some previous topics. So like when we were doing the in-class office hours things, one of the questions that came up was, if the AP exam is only going to be multiple or a free response section, 45 minutes long, if it's only 3 multiple or free response questions, like how do they incorporate all of the different content areas in that? Well, this is one of those ways. So here we have a free fall question, linear motion, and kinetic energy and work all incorporated into one, like very brief 4-part problem. So this is likely more along the lines of what an exam question might look like, where it incorporates all of these different concepts. So we have a ball, mass of 2.4 kilograms, and it's dropped from the top of the building that's 96 meters tall. So that delta x is going to be negative 96 meters, assigning negative direction as down. Because this is a falling object, I also know its acceleration is going to be negative 10 meters per second squared. So that's all good information. Dropped from rest, v naught is 0 meters per second. I want to know the time it takes to reach the ground, the velocity when it reaches the ground, the kinetic energy, and how much work would be required to lift it back up. So for part A, time is my unknown. In this case, given my known variables here and assuming no air resistance, the easiest way to do this is to think of this as just a standard free fall problem. Given this given information, probably the most straightforward equation for time would be delta x equals 1/2 at squared plus v naught t. And remember that equations like this one are only usable when you have uniform acceleration. And because this is a free fall problem, I do have uniform acceleration. I also know that V initial is 0, so that this term is going to be eliminated. So from there, I can plug in the rest of my work. Negative 96 meters equals 1/2 times negative 10 meters per second squared times t squared. And t, if you plug that into your calculator, comes out to be 4.38 seconds. So that's my time to hit the ground. For velocity, again, a couple of different ways you could solve for this. One way you could solve for velocity here, and this is final velocity, remember, would be to use your v squared equals v naught squared plus 2a delta x. If I didn't know time, that would be the way to go. But now that I've already solved for time, given that, the easiest way to solve for final velocity would be v equals v naught plus at. Because again, I know that this v naught is 0. So this is really as simple as multiplying the time by 10. So my final velocity is going to be negative 43.8 meters per second. Again, negative because it's in the downward direction. So now I've got my final velocity. Now I can solve for this part C, which is asking me about the kinetic energy at that bottom point. So that's going to be 1/2 mv squared. Plugging in, chugging out. 1/2 times my mass of 2.4 times my negative 43.8 meters per second squared. And I get a kinetic energy at the end of 2,302.13 joules. 2302.13 joules. It's worth noting too, since we're looking at this, energy is a scalar quantity. Energy does not have a direction. And so that means that energy itself should not be able to be negative, right? Relativistically, it could be. For example, you could have a negative GPE if you define height 0 as above your ending point, for example. But that's all relative position, right? An object can't have less than 0 ability to do stuff. And that's illustrated in the kinetic energy formula with the fact that the velocity is squared. And because it's squared, the value for kinetic energy is always going to be a positive value because mass is scalar, so positive, and velocity, even if it can be negative, gets squared, eliminating the sign. And then lastly, how much work would be required to lift this back up? So if it gains 2,302 joules of energy as it falls, that means it must have started with that much energy at the top, right? Because that's the kinetic energy that it has at the bottom. And so work being the change in energy, that work done would have to be the equivalent of this kinetic energy here, 2,302.13 joules. You could also solve for that using the force and displacement of this. So you could say the force required to lift it back up would be equal to its weight. So that would be 24 newtons multiplied by the height of 96 meters would still give you a work done of 2304, which is, close enough here. The difference here comes from the fact that I rounded. So yeah, you could solve for the work done that way as well, but it's easiest in this case to just think of work as change in energy. Moving on to the last problem, we have this cart. Again, we're given its mass. That's useful information, 2.5 kilograms. We're given information about this inclined plane as well. So let's draw this a diagram of this situation because I think it's useful. So here we have some given information. Let's say my cart starts at the top of this ramp, and the ramp itself has a length of 3.3 meters. So in the context of this diagram, that would be the hypotenuse of the triangle. And the angle of this ramp is 18.5 degrees. So that's useful information as well. The delta x total here then, as the cart goes down the ramp, is going to be 3.3 meters. Theta in this case is 18.5 degrees. And what I'm looking for in this question is the time it takes to get to the bottom, the velocity at the bottom, and the kinetic energy at the bottom. So there's a simple way to solve this problem once we get into conservation of energy type stuff. But at this point in the assignments, we haven't covered that yet, so I'm not going to solve it that way. That the way that we would solve this, given what we know at this point in the lesson sequence, is by finding that acceleration component that's down the ramp. So again, we've done this problem a bunch of times, right? The accelerating vector here is going to be the force of gravity, which is operating at an angle to the plane itself. So the actual component of acceleration, or the force that's causing this acceleration, is just the parallel component Fg in the x direction, where x direction is defined as down the ramp. In other words, it's going to be a fraction of the acceleration due to gravity. So the acceleration down the ramp in the x direction is going to be the parallel component of the acceleration due to gravity. So that's g sine theta in this case, where the acceleration is going to be 10 times sine of 18.5 which is 3.17. So that's my acceleration down the ramp. And once I have that information, I can get to solving part A for that time. Again, I can use the equation delta x equals 1/2 at squared plus v naught t, given that v naught is 0 again. So as with the last problem, this expression goes away, and I'm left with a delta x of 3.3 meters equals 1/2 times 3.17 meters per second squared, t squared. And t, solving for t, 3.3 times 2 divided by 3.17 square root. Ends up being about 1.44 seconds to get down the ramp. Finding part B, the velocity at the bottom of the ramp, again, multiple ways you could solve this problem using kinematics, but the easiest way here, again, v is my unknown, is to just use v equals v naught plus at. Again, v naught is 0, so that term goes away, and so it's just multiplying acceleration and time together. V equals 3.17 times 1.44. And that's about 4.57 meters per second. Lastly, kinetic energy. Now that I've got that information, kinetic energy is my unknown. That's going to be 1/2 mv squared. 1/2 times my mass, which was 2.5, times 4.57 squared. And that gives me a kinetic energy at the bottom of 26.15 joules. Final answer. Yay! All right, and here, just for your viewing pleasure, here is a picture of a turtle. There you go. Enjoy.